Hello, today we have learned the tenfold classification of topological insulators and superconductors. So this table here is pretty much the summary of the day. Okay, so in closing, let me make a few comments. First, this is the periodic table of topological insulators and superconductors. So this is the periodic table of chemical elements. Okay, so when people first made the chemical periodic table, some elements were not yet discovered. Nevertheless, they conjectured the existence of undiscovered chemical elements together with possible chemical properties. And in fact, later they were experimentally discovered. So one may say we are in a somewhat similar situation here. So in this table unifies many known and existing topological states of matter. But however, there are also undiscovered topological states of matter predicted by the periodic table. For example, symmetry class C1 in 3 dimensions, the table says there is a non-trivial topological superconductor here. And symmetry class C1 is a symmetry class of singlet superconductors with time reversal symmetry. So the topological singlet superconductor in class C1 has not yet been discovered. So anyway, as in the chemical periodic table, it is an interesting challenge to find a physical realizations for all entries in the periodic table. Okay. The second comment is about the other symmetries. So in the opening video, I emphasized that symmetries in the tenfold classification are carefully chosen, and that is true. But however, it is still possible to include more symmetry conditions than time reversal, particle Hall, and chiral symmetries. From solid-state physics point of view, natural symmetries to think about are symmetries of a crystal, and in fact, topological phases can exist in the presence of or because of crystalline symmetries. Such topological states of matter are widely called topological crystalline materials. For example, topological crystalline insulators have been experimentally discovered recently. So I think it is reasonable to expect that there will be more discoveries of this kind in the future. But I would, however, emphasize that what we have learned today, like the techniques and the concepts developed in the original tenfold classifications, are basics even in the presence of other symmetries. And they can be suitably generalized and extended to discuss various kinds of topological crystalline materials. Okay. The final issue I want to mention is the effect of interactions. And of course, the interaction effects in topological phases of matter in general are quite non-trivial problems. But however, in certain cases, it was shown that interaction effects invalidate or modify the tenfold classification presented here in this table. So for example, class BD1 in 1 dimension, the table says the classification is an integer. But however, once you include interparticle interactions, it was shown that this classification is actually given by Z8. Not integer in the presence of when you have interparticle interactions. And there are more known examples of this kind. And although I'd say we do not yet have complete theory of interacting topological phases with symmetries, there have been a lot of recent activities concerning the effect of interactions, and we just started to learn the interaction effect in classifying topological phases of matter with interactions. So that's all I want to say. So thank you for your attention.